Good afternoon. Good afternoon, everyone. I do hope that you can hear me loud and clear. Let me share the screen. Hopefully it works. Welcome, everyone. My name is Vladimir Gurevich. I'm working for Intel company as a principal engineer. I'd like to tell you about programmable high-speed commutators and switches. And the previous presentation actually acted as a precursor for me. Dmitry told you where these switches are being used, so the transition would be very smooth. Some notice and disclaimer from our lawyers who warn that, and I will skip that, but I just have to show that. What I'd like to tell you about, why these microchips are needed, the ones which Intel produces, and how they may be used and what for. Secondly, let's speak about how to build them, what is inside, why they are now possible with the current state of the art, and let me tell you how it may be programmed using P4 language, and what can be done next with that, and hopefully we'll have time for Q&A. I'd like to start with the following. Network technologies, that's a very interesting thing. On the one hand, people try to invent something new, and there are a lot of reports, both at that conference and elsewhere. People were speaking about some alternative approaches to different things, and that's a difficult problem. Until recently, people thought that no new technologies are needed because there are a lot of generally acknowledged standards. And once you have generally acknowledged standards, why you have to reinvent the wheel? But there are now progress drivers. For instance, large-scale data centers such as Yandex, Facebook's, Google's, major internet providers also give it a try to build something in-house, and governmental offices and agencies also are part of the process. What happens? First, we had a very disintegrated internet. Everyone would be building something on their own, and there was no connection in terms of standards and protocols. But now, the processing done by big centers, data centers, and on the one hand, people would need the scale, which they were lacking before. They would need the flexibility. People try to make sure that their problems are solved. Energy efficiency has become a big problem, which has to be addressed. And on the other hand, this centralization allows to get away from the standards and to get off the beaten track to offer something new. From the presentations which I listened to prior to my speech, I only got convinced that people all the time try to do something on their own. But the architecture of the networks are quite conservative, and it is very difficult to think of something new, and it is even harder to bring that into life. A regular software world looks very simple, so once you have certain idea, you just buy a simple out-of-box equipment or facility, for instance, plug-and-play chip, or if you have to, actually, you may buy a regular computer or a virtual machine in the cloud, and there are lots of programming languages to help you write your own software, and that's it. So you can make profit. You may take that to the bank, but in the network world, everything is structured differently. You cannot do anything on your own, therefore you go to the network equipment developer, begging him to do something. And the developer would tell you, you see, these things are good, but in reality, As the previous speaker has said, actually, whatever you do to the box, it will still not perform the functions of a microchip. So you have to actually approach Miranox or Broadcom to develop a microchip to add new features. And they will say, yes, actually, these guys look nice, but usually microchips are developed not only to make it work faster, but it will take a little bit more than 2 years to add new functionality. We are waiting for 2 years, and more ideas will come to us. And we forget about the old idea and we do something else. We switch to something else. So it happens so that networks are quite conservative, and changes can hardly take place there. The popular wisdom said that either we are using programmable units, so you can, for instance, write your own software, but usually these solutions would be several hundred times slower, and it would be more costly, it would be more energy intensive, etc., etc. Here is where Intel may help. It all started with Barefoot Company, the one which brought me to Intel as well. We decided that it's no good. And in essence, this problem is not so difficult, it can be addressed. What observations we made? First of all, the data plane algorithms are quite simple. So we have to change the headers to calculate something, to assign something somewhere, transmit something somewhere, and to get rid of the headers. This is the only thing you have to do. You have to manage the commutator's state. For switch, this is quite easy. Switches would need some external components, and we realized that it is not very difficult to run them. I will tell you in more detail how.
Secondly, and that's also important, is that those operations can be parallelized, and every operation consists of many simultaneous operations, because many fields are processed independently. And furthermore, high productivity is where we can build a long conveyor. The longer the conveyor is, the more packets are processed on it. And most importantly, this should be programmed in a high-level language, because if we do this at a register level or something, then nothing can be done. So how is it organized in real life? It all starts with this abstract picture. This is a protocol-independent packet processing. And this structure works the same for every switch. When the packet goes to your switch, first it's the disassembler or parser of the packets that starts working with that. So this parser identifies the network headers there. It's a pretty simple machine. It looks at the headers, understands that this header is followed by some tags, and then it understands that after that tag there is a TCP and so on. So this parser splits the packet into separate headlines. And we are still accepting the packets. Those packets can be very long, but we do need to process the header. And those headers go to a conveyor, which does the same operation, match action. How does it work? It's very simple. We have a table, and we do a search in those tables. You need to look at the destination address. This will be in your search. Then you need to find the output port, for example. then you can do something else. Or you can use IPv4 to find the destination address, then you check the control sum, and so on. So what happens here is that this data starts going through this conveyor. And at every stage, there is a new interim result. We remove some of the headers, we add others, and there may be a different number of such headers in a switch, up to 20 actually. And finally, we only have the last 3 headers which underwent all this processing. And they go to a deparser. There, they are put together with the body of the packet, and there are new headers stuck on them, and then this packet goes for further processing. So this is the architecture we have. I hope it's pretty simple. What's particular in it? The packets are only moving forward, which is why the duration of processing is always the same. There are no cycles here. If you need a cycle, then you need to have a loop back in the port. And within each stage, there are many tables, not just one of them. We can do parallel search in the tables. And most importantly, with every cycle, there are new packets coming and processed. It's very easy to parallelize those actions. The bigger the envelope is, the more packets we process simultaneously. How do those tables function? They are real tables. They look like all other tables everywhere. They are rectangular. And they consist of 3 parts. The key, with which we do the match, the action code, that's what we need to do next, and the parameters of the action. Those tables are programmed by your control player. And unlike standard tables, these tables have an additional line that is actioned by default in case the key has not been identified. And then all those components come together linked by a bus. And they are called metadata. Then some fields are chosen that are of interest to us. For example, the destination MAC address or VLAN ID. Then there is the search key, and this search key is composed in order to do a search in the table. And we have 2 types of an answer. Either we have found this answer in the table or we haven't. And if we haven't, then we used the by default action and parameters. And then there is a small multiplexer which chooses between the 2 possibilities. And then it goes to the action execution block, where we do those additional actions. And we can use any headers and metadata that are available, and the results go once again to the same bus. And it's very nice because we can work on those tables in parallel. That depends on how much place we have in our microchip, and we can put those tables one after another or in parallel. It's very easy to work with many tables in parallel simultaneously. So that was some abstract architecture, but when we build a real device, we need to have a certain mix. On the one hand, we need programmable blocks, an input and an output conveyor or pipeline. The input pipeline has an input packet, then there is the parser and the deparser of the packets. And in the output pipeline, we also have some operations. And between those two conveyors, there is a packet interface which delivers the data inside the pipeline or conveyor pipeline. And then we have some data which goes out of the input pipeline. And finally, we have a packet replicator and a traffic manager, which are in the middle. And here we buffer our packets. And here we can create a multicast to make sure everything works okay. And we talk with these devices via special system metadata. They are well-known variables. If the packet comes out from the input interface, the input interface sends us the time label, and then it sends us the number of the port via which we got it. If we want to send the packet to another port, then there is another known variable which tells the system to send this data to port 5, for example. So that's about it. As for the real microchips, we built the Intel Tofino microchip in 2016. It has 260 ports, 25 gigabits each of them, and they can be put together in different combinations. The frequency is 1220 megahertz. And the interesting thing is that this chip was the same as any non-programmable chip in terms of costs. And we already have Intel Tofino 2, which has a productivity that is twice as high. The technology is 7 nanometers. This chip can carry out more difficult operations. It has more pipelines and so on. The Tofino has 4 pipelines, not one pipeline, but 4. So it's like a 4-core processor, but the ports are linked to a certain conveyor. And what happens is that they have this traffic manager and packet replicator, which are attached to all the 4 pipelines, which is why data can be moved from one pipeline to another pipeline. We make a choice where to send our data at the beginning and in the middle as well. What happens inside? It's pretty funny. You can see some nice animation here. The data comes in, there is buffering, and in each pipeline, actually I show you just one conveyor, right? Just one pipeline. In each pipeline, there are 18 independent buses, 100 gigabits per second in each of them. Then those packets go to the processing pipeline. And what is important is that those packets only use a part of those resources, those that are designed for input processing. And then this data is bufferized and goes to the output pipeline where there are passes. And then this data goes through the same stages, but the color of the resources is different. They are light green here. So as a result, our software can be very flexible. Some software can have or needs to have more resources. It depends on the way your compiler compiles this data. But anyway, the program, the software is very flexible. And you can see here that at each cycle, there is one packet coming in, one packet coming out, and the whole device works with 2 pipelines at the same time. And we have several dozens of packets being processed at the same time. And one pipeline can process up to 720 packets at the same time. There are some other devices here. I'll tell you later about them. One important thing in Tofino is the header and metadata bus, which exchanges all information, and data is put in containers or registers, which can be 8-bit, 16-bit, or 32-bit. In this bus, there's a total of 4 kilobytes. Of course, the young generation doesn't know what is less than 1 gigabyte, so it seems to be little. But just think about the Fino. What is it? It is a 4096 bit processor. So all those 4096 bits are processed at the same time. And we have 224 containers like that. And what happens is that in each container, there is a small arithmetic device or calculating device. Let's look at this input, which works with our headers. You can see that a lot of operations are done in parallel. So if you look at this code, you can see that each line is an operation with a separate code. And what happens here is that each out of those 224 containers has its own calculation instruction. And the instruction is written in BLIWs. They are some long words. There are 224 sections or words, and in each word there is an instruction for a specific computation device. And within each table there is an indicator to a relevant word. And then we use the OR logical operation. And we can fulfill up to 224 operations simultaneously within each cycle. So our frequency is more than 1 gigahertz. So this device really runs in parallel. We also have the match action unit block, which has special multipliers. And as a result, we can do search in a large number of tables in parallel, up to 16. And here I would like to show you a small visualization of what's located inside. There are some multiplexers. One multiplexer uses those decamps or triple tables, then this data goes to tcams, and then it goes to hash bits. This hash device can generate hashes. And then we have the SRAM blocks, where we can put keys, data, counts, special registers, and so on and so forth. Here we have those long words that are instructions, and there is a lot of interesting logic here. For example, these are gateways which ensure special operations such as the if operation and so on. So we have such components in each of the 12 blocks, and it's programmed in the P4 language. It's a pretty simple language which has some data types with which we are familiar. There are bit sequences, there are numbers, and each length in the bit has its own type of data. And of course, there are expressions, there are parsers, and there are standard controlling structures, such as the if operator, the switch operator. We don't have a cycle operator, but those controls are used to run those parsers and deparsers and other elements. The interesting thing is that P4 can support different elements, for each particular microchip, because the manufacturer shows what elements can be programmed in a microchip. And this language also supports the so-called external blocks or externs, which describe different functions which can't be normally described in a language. This is the P4 code. I already showed you one example. There's another example. You see that there is nothing difficult here. In the RFC, you can write your own header. Here you write what fields are used for keys, which fields are used for actions, what the size should be, and what should the default action be. And the action is described as in many other languages. Here you can see the parameters, and here you write what needs to be done. The important thing about the language is that it's not a proprietary language. It's an open language. And I'm a member of the language development group, and it is done under the auspices of Open Network Foundation. And it's all done by the p4.org organization. And here you can see the members of this organization. They come from different places. There are hardware developers, microchip developers, and manufacturers, organizations, and end users. The membership is free of charge, so I invite you to join this organization. We already have some members from Russia as well, and some of them have started looking into it. Here you can see the P4 application areas. One thing that we discussed, that was discussed by Dmitry at the previous presentation, is machine learning, of course. And we also can do different things with P4. Along with the normal routing and switching, we can build smart firewalls or balancing or telemetry, because it's very easy to use interim results and send them from the switch to the packet and so on.
And finally, to conclude my presentation, I just wanted to say that what I would advise you to do. First, suddenly such programmable commutators open a wide spectrum for you. You have just to give it a try, to test. Try doing something. You may use whitebox and write your own commutator and write your own extension or your own control plane, or do whatever you need. Secondly, come to Barefoot Academy, and in 2 weeks it will be called Interconnectivity Academy. This is an institution which I'm heading, where we train people to program, and if you're working in some organization, you're invited to join P4.org and to do more with the programmable commutators. Thank you so much. Vladimir, thank you so much. We have time for one question only. And I will abuse my role as a moderator to pick one question. So let's discuss what a rookie needs in order to get started. There was a question, advice and AD for a rookie. And software, you can start with VPP or something else. You want just to start from scratch, to start with the simplest thing. Before to Torque, they have a simulator of behavioral model version 2. And this is a software switch. But if you want to start working with tough-in and really to programming of real chips is different from programming of abstract software switches, because the number of limitations and things you have to know in order to program a chip is huge. What you can do? You can turn to Intel, and after you sign a non-disclosure agreement, and for the research, organizations and projects who have their own program. This is for free. When you sign an agreement or a document, then you get an access to emulator of the chip and to the P4 Studio with a visualizer, calculator, and many other things. You can start working with that. And in many cases, you can just buy white boxes with the Tafina installed, and on top you may actually install P4 Studio, and you can start working with that. So it's not different from just buying a computer, installing Linux, and start working with that. So it looks very much the same. Thank you so much. Please go to our chat. There are lots of questions. Unfortunately, we cannot spell them out. Yes, I saw the flow of the questions there, so let me start answering them. Thank you so much.